In lecture 30, we will discuss the hyperbolic functions, which are three. The hyperbolic sine of x, defined as e to the x minus e to the minus x divided by 2. Then we have the hyperbolic cosine of x, e to the x plus e to the minus x divided by 2, and the hyperbolic tangent of x equal to the hyperbolic sine of x divided by the hyperbolic cosine of x, which is simply e to the x minus e to the minus x divided by e to the x plus e to the minus x. And all these are defined for every x real number on the entire line. So these are the three hyperbolic functions. Let's start by discussing the symmetry of these functions, which is to say that we want to establish if these functions are even or odd. Okay, let's start with the hyperbolic cosine of x, and let's see what is the hyperbolic cosine of minus x. Well, if we just replace minus x in the expression of the hyperbolic cosine of x, we get e to the minus x plus e to the x divided by 2, which is nothing else than the hyperbolic cosine of x. So this shows that this hyperbolic cosine is an even function. Instead, the hyperbolic sine of minus x is e to the minus x minus e to the x divided by 2, which, if we can put minus in front of the fraction, we get e to the x minus e to the minus x divided by 2, and this proves that the hyperbolic sine of x is an odd function. Finally, the hyperbolic tangent of minus x is equal to e to the minus x minus e to the x divided by e minus x plus e to the x. And again, factoring out minus, we have e to the x minus e to the minus x divided by e to the x plus e to the minus x, which proves that the hyperbolic tangent of x is another odd function. Let's now pass to the derivatives. The derivatives of the hyperbolic sine of x would be basically the derivative of e to the x minus e to the minus x divided by 2, which is easily calculated as e to the x plus e to the minus x divided by 2. So this is nothing else than the hyperbolic cosine of x. Instead, the derivative of the hyperbolic cosine of x, which is e to the x plus e to the minus x divided by 2 prime, well, this is e to the x minus e to the minus x, which is the hyperbolic sine of x. Finally, if we take the derivative of the hyperbolic tangent of x, remember that this is the derivative of the ratio between the hyperbolic sine of x and the hyperbolic cosine of x. And by just applying the rule of derivative of a fraction, we have hyperbolic cosine square of x at the denominator, and then we have the derivative of the sine hyperbolic of x, which is the cosine hyperbolic of x. So what we get is the hyperbolic cosine square of x minus the hyperbolic sine of x squared, which, if we separate this into two fractions, we simply get 1 minus the hyperbolic tangent of x. Now that we know the derivatives, we can attempt the Taylor expansions. In x not equal 0. Let's start with the hyperbolic cosine of x, which we know is 1/2 e to the x plus e to the minus x. This is easily obtained by just using the expansion of e to the x, which is 1 plus x plus 1/2 x squared plus 1/6 x to the cube plus 1/24 x to the 4, and so on and so forth, right? Then we have the expansion of e to the minus x, which is 1 minus x plus 1/2 x squared minus 1/6 x to the cube plus 1/24 x to the 4, and so on and so forth. So we immediately realize that x and minus x cancel out. 1/6 x to the cube and minus 1/6 x to the cube, and in other words, all the odd powers of x will be cancelled out, and then we will be left with 1/2. If we just add all the remaining terms, we easily see that we have 2 times 1 plus 1/2 x squared plus 1/24 x to the 4th, and so on and so forth. So this is nothing else that 1 plus 1/2 x to the square plus 1/24 x to the 4th, so on and so forth. And notice that this is the same as cosine of x with positive coefficients. In other words, instead of having alternating sign at each and every term, we only have positive coefficients. Let's now carry out the Taylor expansion for the hyperbolic sine of x, which is 1/2 e to the x minus e to the minus x. Well, in this case we have 1/2. First we have the expansion of e to the x, which is 1 plus x plus 1/2 x to the square plus 1/6 x to the cube plus 1/24 x to the 4th, so on and so forth. And then we have to subtract the expansion of e to the minus x. So we have minus 1 plus x minus 1/2 x to the square plus 1/6 x to the cube minus 1/24 x to the 4th, and so on and so forth. And this time we immediately see that the terms that will disappear are exactly the even powers of x. And in fact 1 and minus 1, 1/2 x to the square, and minus 1/2 x to the square, 1/24 x to the 4th, minus 1/24 x to the 4th, and we can easily conclude then that this is equal to x plus x 1/6 x to the cube plus 1/120 x to the 5th, so on and so forth. So again, we notice that we have the same as sine of x with positive coefficients. Now, by looking at these two Taylor expansions, we realize that if we sum hyperbolic sine of x and hyperbolic cosine of x, what we get is exactly the Taylor expansion of the exponential. So we can make the following observation. The hyperbolic sine of x plus the hyperbolic cosine of x, which is e to the x minus e to the minus x divided by 2, plus e to the x plus e to the minus x divided by 2, and if we sum them all together, what do we get? Well, easily we realize that this is e to the x, and this is true for every x into the real numbers, and this is consistent with our Taylor expansions. And now we come to a fundamental relation between these two hyperbolic function, hyperbolic sine and hyperbolic cosine. And so let me start from the square of the hyperbolic sine of x, which is e to the x minus e to the minus x divided by 2 square. Well, if we take the squares of the numerator and denominator, well, we have 4 at the denominator, and we have e to the 2x minus 2 plus e to the minus 2x, right? And let's do the same for the hyperbolic cosine. We take the square, which is e to the x plus e to the minus x divided by 2 square, and what we get, 4 at the denominator, and e to the 2x plus 2 plus e to the minus 2x. So if we now take the square of the hyperbolic cosine of x minus the square of the hyperbolic sine of x, we immediately have, in one single fraction, we have e to the 2x plus 2 plus e to the minus 2x then we have minus e to the 2x plus 2 minus e to the minus 2x, and we can cancel this and this, this and this, and so we get this fundamental relation, which is worth putting in repeating again. So we have that the square of the hyperbolic cosine of x minus the square of the hyperbolic sine of x is equal to 1, and this is true for every x in R. This is the equivalent of the trigonometric fundamental relationship between the sine and the cosine. The only difference is that now we have a minus, okay? Instead of having the sum, we have the difference of the square, which is equal to 1. And now that we have this, we can also rethink about the derivative of the hyperbolic tangent of x. Remember that we said that this derivative was equal to the hyperbolic cosine square of x minus the hyperbolic sine square of x divided by the square of the hyperbolic cosine of x. But now we can rewrite this as 1 divided by the hyperbolic cosine square of x, which is another relation very similar to the trigonometric counterpart between for the derivative of the tangent of x. Let's explore even more this analogy with the trigonometric function, and let's see if we can find the duplication formula for hyperbolic functions. So in other words, I will be looking at the hyperbolic sine of 2x, and by just applying the definition, we have e to the 2x minus e to the minus 2x divided by 2, right? Which can be also expressed, because we have a difference of squares, we can split this, the numerator, into e to the x plus e to the minus x, that multiplies e to the x minus e to the minus x, right? But these can also be expressed as e to the x plus e to the minus x divided by 2, and I immediately recognize an hyperbolic cosine of x. What I need now is an hyperbolic sine of x, which can be easily expressed as e to the x minus e to the minus x divided by 2, and then I need to multiply by 2. So what we get is finally that this is simply that the hyperbolic sine of 2x is equal to 2 times the hyperbolic sine of x times the hyperbolic cosine of x, which is exactly the analogous for the hyperbolic function of the duplication formula for the trigonometric function. Let's see if we find a similar expression also for the hyperbolic cosine of 2x. Well, in this case, we have e to the 2x plus e to the minus 2x divided by 2, right? And we can say that this is e to the x plus e to the minus x all square, but then we need to, of course, subtract 2, right? And so let me express this as e to the x plus e to the minus x square divided by 2 minus 1. Okay, and now we can use the fundamental relation and say that this is e to the x plus e to the minus x all square divided by 2 minus hyperbolic cosine square of x plus the hyperbolic sine square of x, right? And but this is nothing else that 2 times the hyperbolic cosine square of x minus the hyperbolic cosine square of x plus the hyperbolic sine square of x, and finally this gives me the hyperbolic cosine square of x plus the hyperbolic sine square of x. So we have another similarity with the trigonometric function, because we can conclude saying that the hyperbolic cosine of 2x, so the duplication formula for the hyperbolic cosine is simply given by the hyperbolic cosine square of x plus the hyperbolic sine square of x, fully similar to the analogous expression for the trigonometric functions. Now that we have established important relationships between the functions, it's time to have a look at the behavior of the function, and in particular to the monotonicity of the function. In fact, we'll see that, let's start with the sine of x, okay? So the first property is that the hyperbolic sine of x is strictly increasing for every x in R. In fact, we know that hyperbolic sine of x is defined for every x on the real line, and we are saying that this function is strictly increasing. So this is the first property. Let me highlight this first property, and now I will prove this. Now, why is that? Well, the thing is this, that if you consider the expression of the hyperbolic sine of x, right? So this is given by 1/2 of e to the x, right? Plus we have minus 1/2 e to the minus x, okay? And now let's think about the e to the x times 1/2. What is the behavior of this function, and what is the behavior of this function, right? So, well, for this function, we have that 1/2 e to the x will be a function like this, with this equal to 1/2. So clearly, this is strictly increasing, right? So let's see the other part. Let me first consider 1/2 e to the minus x. Okay, so this would be 1/2 e to the minus x, so with this 1/2. So this would be 1/2 e to the minus x. But we need to mirror this function with respect to the x-axis, so that we get exactly this. And of course this is minus 1/2, and this would be minus 1/2 e to the minus x, which is another strictly increasing function. So we have now proved that the hyperbolic sine of x must be a strictly increasing function. Let's see what happens instead for the hyperbolic cosine of x. Okay, now it turns out that also the hyperbolic cosine of x is strictly increasing for every x into the real numbers. Okay, well, not really. This is true only for x larger than or equal to 0. Okay, and I will prove this now. Well, the proof of this is a little bit more involved. Okay, so let me give the proof of this fact. Okay, now proof. So to prove that the hyperbolic cosine is strictly increasing, we need to pick some y larger than x, okay, larger than or equal to 0. Okay, so we're saying that basically we are in a situation where we have somewhere y which sits to the right of x, and x is of course larger than or equal to 0. Okay, we are in this part of the plane, and we want to now prove that the hyperbolic cosine of y is strictly larger than the hyperbolic cosine of x. Okay, so this is what we want to prove. We want to prove that if the hyperbolic cosine of x is here, well, the hyperbolic cosine of y must be somewhere above that level. Okay, now this is what we wish to prove. No, we wish to prove that these two things. Okay, now the fact that the hyperbolic cosine of y is larger than the hyperbolic cosine of x is just like saying that e to the y plus e to the minus y divided by 2 is larger than e to the x plus e to the minus x divided by 2, right? And well, of course, this is just like saying that we can just remove the 2, okay, multiplying the left hand side and the right hand side by 2 doesn't change the equality. So we need to prove that e to the y plus e to the minus y is strictly larger than e to the x plus e to the minus x. Now let's put e to the y to be equal to b. Okay, and we know that b is going to be a positive number because it is just the power of e. Okay, and let's put that e to the x is equal to a. Now we know something. We know something that we know that because the exponential is a function that is always above 1. Remember what is the shape of the exponential, right? So if we have the exponential, this is e to the x, okay? The generic e to the x. Now, it turns out that if we have that x is here and y is here, right, and we know that y is to the right of x, we certainly know that this is e to the x, this is e to the y, and they both are larger than 1. So we can write this. We can write that b, which is e to the y is larger than a, which is larger than or equal to 1. Okay, we can write this. Good. Now let's replace e to the y with b and e to the x with a. What we got is b plus 1 over b larger than a plus 1 over a, which in turn means b squared plus 1 divided by b larger than a squared plus 1 divided by a, right? And of course this is just like saying that a b squared plus a is larger than a squared b plus b. Okay, and now again let's reshuffle all these terms, and we can easily factor out ab on the left hand side, and we have b minus a, right, plus minus b minus a. This should be larger than 0, right? And this again is by factoring b minus a, what we got is ab minus 1 that multiplies b minus a. This should be larger than 0. So in other words, we can also reinvert all these arrows, okay, because they are sufficient and necessary conditions, right? So if we prove that this last inequality is correct, we can finally prove the initial statement. Okay, we can finally prove this basically, right? But this is easily correct because we know that by the first thing that we said here, we said that b is larger than a, so that proves that this is larger than 0. And because a and b are both larger than 1, well, certainly the product of AB will be larger than 0 as well. Sorry, larger than 1. So this proves that the difference AB minus 1 is larger than 0. So finally, we have proved that the initial statement was correct. Now at this point we are ready to attempt plotting the graphs. So these are the graphs of the hyperbolic functions. Let me start with the hyperbolic cosine. Then we'll plot the hyperbolic cosine, and finally the hyperbolic tangent. Okay, so the hyperbolic sine of x, hyperbolic cosine of x, and hyperbolic tangent of x. Okay, now we know that the hyperbolic sine of 0, remember that the hyperbolic sine of 0 would be basically e to the 0 minus e to the 0 divided by 2. So clearly this is 0. Okay, so we know that the graph of the function will pass from 0. We also know that the tangent at 0 is going to be basically the derivative, okay, of the hyperbolic sine. Remember that the derivative of the hyperbolic sine is nothing else than the hyperbolic cosine, right? And the hyperbolic cosine at 0 is going to be 1, okay, because it is e to the 0 plus e to the 0 divided by 2, so clearly this is 1. And we also see that the limit of the for x that goes to plus infinity of the hyperbolic sine of x would be nothing else that the limit of e to the x plus e to the minus x, minus e to the minus x divided by 2, but for x that goes to, let me say, plus or minus infinity, clearly e to the minus x will become negligible, so we are just left with plus or minus infinity. So we can say that, first of all, we can attempt, if this is the bisector, we see that the hyperbolic sine will have a behavior like this. Right, so it will go to plus infinity for x that goes to plus infinity. It will go to minus infinity for x that goes to minus infinity. It is always increasing, okay, and has a tangent that is just a bisector in the origin. And similarly, we can attempt the plot of the hyperbolic cosine of x. Now, let me start by finding the hyperbolic cosine of 0. Well, we know that this is 1, okay, so let's say that this is the point 1, and remember that the hyperbolic cosine of x we prove to be an even function, so we can limit ourselves to the study of the function for x larger than or equal to 0, and then we'll mirror this with respect to the y-axis. And first of all, what is the tangent in for x equals 0? It will be the hyperbolic sine of 0, which we know is 0. So at this point we know that the tangent at 1 is going to be exactly this. So it will have horizontal tangent. It will go to plus infinity, because if we take the limit of the hyperbolic cosine of x for x that goes to plus infinity, this will be just the limit as x goes to plus infinity of e to the x plus e to the minus x divided by 2, but this will be neglected. So this is plus infinity, so we have this behavior for x that goes to plus infinity, and now we can just mirror with respect to the y-axis, and this is the plot for the hyperbolic cosine of x. Now, when it comes to the hyperbolic tangent of x, the first thing is that what will be the hyperbolic tangent at 0? Remember the expression. We know that this is the hyperbolic sine divided the hyperbolic cosine, but the hyperbolic sine is 0, so we immediately realize that this function has to pass by 0, right? And also, let's take the limit of the hyperbolic tangent of x as x goes to plus infinity. Remember that we proved that the hyperbolic tangent is an odd function, so we can limit ourselves to the x larger than or equal to 0, and then we'll basically revert the function with respect to the origin. Okay, good. So this is equal to the limit as x goes to plus infinity of e to the x minus e to the minus x, e to the x plus e to the minus x. But again, we can easily neglect these. They don't count when x gets larger and larger. So this limit is simply equal to 1. Okay? So we can draw this line, and we see that if this is 1, the function will get closer and closer to 1 when x goes to infinity. How about the tangent derivative? So what is the slope of the graph when the graph passes by the origin? Well, we know that the derivative of the hyperbolic tangent is just given by 1 over cosine square, right? So if we take 1 over the hyperbolic cosine square evaluated at 0, which turns out to be exactly 1, again we have that the tangent will be, the slope of the graph will be exactly the bisector. Okay, and at this point we only have one possible behavior, and the possible behavior that we have is exactly this. And of course, if we take the symmetry with respect to the origin, we have this is minus 1, so the other branch of the function is going to be this one. Well, to be fair, we have used another thing to plot the graph of the hyperbolic tangent, namely the fact that this function is strictly increasing. Let me prove this fact here. Let me make some space here and prove that the hyperbolic tangent of x is strictly increasing for every x into the real numbers. Okay, once again we take y larger than x, and then again we can limit ourselves to the only the positive axis, just because we know that the function is an odd function, right? So, and from this we would like to prove that the hyperbolic tangent of y is strictly larger than the hyperbolic tangent of x, which is just like proving what? It is just like proving that e to the x minus e to the y minus e to the minus y divided by e to the y plus e to the minus y, and this is the hyperbolic tangent of y, is strictly larger than e to the x minus e to the minus x divided by e to the x plus e to the minus x. Okay, and now again we can set e to the y equal to b, e to the x equal to a, and where because the exponential is a strictly increasing function, we know that b is larger than a, right, which is larger than or equal to 1. Okay, we can say that. Now let's replace now e to the y and e to the x with b and a. what we get is b minus 1 over b divided by b plus 1 over b larger than a minus 1 over a divided by a plus 1 over a. And of course this is true if and only if we have b squared minus 1 divided by b and b squared plus 1 divided by b. Well, we can immediately simplify b at the denominator, right? So the left hand side simply becomes b squared minus 1 divided by b squared plus 1. And similarly, on the right hand side we have a squared minus 1 divided by a squared plus 1, which is true if and only if what we get. We multiplied by a squared plus 1 times b squared plus 1. What we get is a squared plus 1 times b squared minus 1 larger than a squared minus 1 times b squared plus 1. And this, if we develop the product, we get at the left hand side a squared b squared, right, minus a squared plus b squared minus 1, minus 1 larger than a squared b squared plus a squared minus b squared minus 1. Okay, so we have that a squared b squared and a squared b squared cancel out, minus 1 and minus 1 cancel out, so this gives me now what? Well, we have b squared minus a squared times 2, right? B squared minus. Now that we have established many properties of the hyperbolic functions, we would like to explore the possibility of building the inverse hyperbolic functions. And let's start our discussion with the hyperbolic sine of x. Well, the hyperbolic sine of x, we just saw it is a function which is strictly increasing, and which implies that this is basically a bijection. So we can say that hyperbolic sine of x is a bijection on the entire real line, which implies that there exists an inverse which we call g from r to r, which will be exactly the inverse. So the hyperbolic sine of x is invertible, and the inverse function now is g of x. We will give a name that resembles and reminds us of the trigonometric inverse functions. We will call this arc hyperbolic sine of x. This is for every x into the real line. Okay, so how do we find this function? Well, what we can say is that if we have an x here, this is the hyperbolic sine, so we know that this y, well, this y is exactly the hyperbolic sine of x. Now, what we wish to find is the function that gives x once that we provide y. So we wish to find x as a function of y. Okay, so this is the problem that we are facing now. Basically, we can rewrite um, this equation, okay, y equal to the hyperbolic sine of x. We can rewrite this as follows. We can, well, the hyperbolic sine of x is e to the x minus e to the minus x divided by 2, and this is equal to y. What we need to do basically to find x as a function of y, we need to solve this equation. So we need to solve in x the following equation. Okay, how can we do this? Well, we first of all we multiply by 2 and we get e to the x minus e to the minus x equal to 2y. And then by setting e to the x equal to a, which we know is larger than 0, right, because it is just a power of e, then we can rewrite the equation as a minus 1 over a equal to 2y, and multiply everything by a, we get a squared minus 1 equal to 2ya, or bringing everything to the left hand side, we get the second degree equation, a to the square minus 2ya minus 1 equals 0. Well, this equation can be solved in a and gives 2y plus or minus the square root of 4y squared plus 4. And simplifying all the 2's, we get simply y plus or minus square root of y squared plus 1. Now remember that a is larger than 0. Okay, so because a is larger than 0, we can only select the plus sign for the square root. Okay, because clearly if we select the minus, we would get a negative. Okay, so this implies that a is equal to y plus the square root of y squared plus 1. Okay, we are almost there now because we just replace the a with e to the x is equal to y plus the square root of y squared plus 1, which finally gives x as the logarithm of y plus the square root of y squared plus 1. But this x is exactly the inverse function that we were looking at, right? Remember that x is exactly the arc hyperbolic sine of y. Okay, so we have now an expression for the inverse function. Now let me just revert the x and y. The reason is that we would like to consider now just a function of x, and so we can conclude our derivation by saying that the arc of the hyperbolic sine of x is given by the natural logarithm of x plus the square root of x squared plus 1, and this is true for every x into the real numbers. So this is the expression of the inverse function of the hyperbolic sine of x. And notice something, that this quantity, right, this quantity here, this is worth noticing, this quantity here is always larger than 0, so this is well defined. In fact, we know that the logarithm can only be defined for positive values, okay? And so clearly this is well defined because the square root of x squared plus 1, of course, is something which is larger than x, okay? So even if x is negative, when we take x plus the square root of x squared plus 1, we always get a positive number. Let's now explore the possibility of building the inverse of the hyperbolic cosine of x. Now, the hyperbolic sine of x, we saw that the graph is this one, okay, with this point being 1. So this is an even function, and we clearly see that this function is not injective over the entire real line, but it is injective on the only on the positive x, okay? And we also see that the image of the function, the y, are this set of all positive real numbers larger than 1. So we can express this as considering this function f. Okay, let me say this: f of x is equal to the hyperbolic cosine of x. Well, this function f sends the entire real line only on the set of positive numbers larger than 1. So we see that the only possibility for x, and this is of course we will select only the one of the two branches, otherwise the function would be not invertible, right? So we can say that this is for we can invert this function. F of x is invertible only for x larger than or equal to 0. So what is the inverse? Well, the inverse would be a function g that goes from 1 plus infinity to 0 plus infinity, right? So we're saying that basically the two sets that we will consider are these two, right? So these are the two domain and codomain of the function and its inverse. So with this in mind, let's proceed and try to follow the same procedure. Let's say that this is x, this will be our y. We would write that y is equal to the hyperbolic cosine of x, and again we want to solve this equation in x. Let's solve in x. How can we do this? Well, we can rewrite the hyperbolic cosine by definition is e to the x plus e to the minus x divided by 2 equal to y, which implies that e to the x plus e to the minus x is equal to 2y. And again, setting e to the x equal to a, but now we know that a is larger than or equal to 1, we can rewrite the equation as a plus 1 over a equal to 2y, and multiplied by a we get a squared plus 1 equal to 2ya, and this becomes a squared minus 2ya plus 1 equal to 0. And if we solve this, we get a equal to all divided by 2, and we get now 2y, okay, plus or minus square root of 4y squared, and this time we get the minus 4. And simplifying the 2's, we get y plus or minus square root of y squared minus 1. And remember again that we need to have that a must be larger than or equal to 1, okay? So this immediately shows that we must have only the positive, right? So we can say that a is equal to y plus the square root of y squared minus 1, because clearly you see that the square root of y squared minus 1 is something less than y. So we wouldn't get a larger which is larger than 1, okay? Right, so with this we can now replace a with e to the x is equal now to y plus the square root of y squared minus 1, which finally gives x as the logarithm of y plus the square root of y squared minus 1. But this is exactly what we were looking for, which is the arc cosine, hyperbolic cosine of y. And by just reverting, as always, the x and y roles, we get that the arc hyperbolic cosine of x is equal to the logarithm of x plus the square root of x squared minus 1. And this is true only for x larger than or equal to 1. And in fact, you see that once again, if x is larger than or equal to 1, the argument of the logarithm is positive, which is consistent with the definition of the logarithm. So, sorry, let me change color. So this is the inverse function for the hyperbolic cosine of x. As a final step, let's look at the inverse of the hyperbolic tangent of x. Let me remind you what is the graph of this function. We know that this function is between these two lines, minus 1 and plus 1, and it is an always increasing function. So clearly this is a bijection from the entire real line onto minus 1, 1 open. Okay, so we can invert only between these two sets. Okay, so the two sets that we are considering now are clearly the entire real line on one side and the open interval between minus 1 and 1. Okay, so we can search for an inverse function g that goes from minus 1, 1 into the real line. And this function g will be what we'll call the arc hyperbolic tangent of x. Okay, for every x in the interval minus 1, 1. And let's follow the usual procedure now. Okay, so we say once again that if we have this x and this is y, well, we say that y is equal to the hyperbolic tangent of x, okay? And we need to solve in x, and we'll go very fast now because we know the process already. We have e to the x minus e to the minus x divided by e to the x plus e to the minus x is equal to y. We set e to the x equal to some a larger than 0, which finally gives a minus 1 over a divided by a plus 1 over a equal to y, right? And this is a squared minus 1 divided by a squared plus 1 equal to y. And this is a squared minus 1 equal to y times a squared plus 1, right? And again, these can be solved in a because we get a squared times 1 on the left hand side minus y, and on the right hand side we have y plus 1. So we find that a squared is equal to y plus 1 divided by 1 minus y. By symmetry, let me rewrite this as 1 plus y. Okay? And remember that y now is in between minus 1 and 1, so this is indeed correct. This is always positive. But this implies that a, to be positive, we need to take only the positive square root of 1 plus y divided by 1 minus y. And replacing a with e to the x, we have e to the x is equal to the square root of 1 plus y divided by 1 minus y, which means that x is the logarithm of the square root of 1 plus y divided by 1 minus y. And this is exactly what we were looking for, the arc of the hyperbolic tangent of y. This, of course, only for y in the interval minus 1, 1. So we can highlight this final result saying that the arc hyperbolic tangent of x is equal. To conclude this lecture on hyperbolic function, we will provide two interpretations. The first is a geometric interpretation of hyperbolic functions, which is very similar to the geometric interpretation of trigonometric function. Okay, the difference is that now we, instead of considering the unit circle, we will consider the hyperbola, and this gives the reason why these functions are called hyperbolic functions. Okay, now let's consider the hyperbola with the equation x squared minus y squared equal to 1. Okay, now this what is the graph of this function? Well, for y equal to 0, x squared is equal to 1, so it will be certainly located in between these two asymptotes, with this being 1 and this being minus 1. Now, actually, we don't need the left branch, so let's remove the left branch, or just put this as dashed line because we will be only using the right branch. Okay, so this is the right branch of the hyperbola x squared minus y squared equal to 1. And notice that clearly the asymptotes are, this is just the bisector of the second and third quadrant, y equal x, and this is the bisector of the second and fourth quadrant, y equal to minus x. Okay? Now, the fundamental observation that we do here is the following. For every number alpha into the real numbers, for every real numbers alpha, there exists a point P on the hyperbola such that the area of the sector of the hyperbolic sector is alpha divided by 2. So let me explain what I'm saying, okay? So I'm saying that for every real number alpha, I can identify a point P on the hyperbola such that the hyperbolic sector, what is the area of this hyperbolic sector? You just need to connect the origin with the point P and then consider this area. So this is the area of the hyperbolic sector, and it turns out that this sector is equal to alpha divided by 2. So you give me any real number alpha and I will find you a point P on this branch of the hyperbola such that this sector highlighted here in white has area exactly equal to alpha divided by 2. Now, of course, if alpha is positive, P is moving basically on the upper part of the branch. If alpha is negative, it will identify negative areas. Okay, so P will be moving downward on this branch of the hyperbola. So we can say now that this point P, what are the coordinates of this point P? Well, these coordinates are hyperbolic cosine of alpha and hyperbolic sine of alpha. So this is basically the connection between the hyperbola and the two functions that we have identified. So let me repeat this concept. You give me any real number alpha and I can find the point P which sits on the hyperbola, okay, such that the area of the hyperbolic sector is equal to alpha divided by 2. And in fact, to prove that this point is just sitting on the hyperbola, we need to verify that its coordinates satisfy the equation of the hyperbola. And in fact, if we have the hyperbolic cosine of alpha squared minus the hyperbolic sine of alpha squared, well, the fundamental equation says that this is exactly equal to 1. So this proves that indeed this point P sits on the branch of the hyperbola. Okay? The second interpretation that we want to give about the hyperbolic functions is a mechanical interpretation. And this is basically the reason why these functions come up so often in analysis and in mechanics. If basically you have an inextensible cable and you attach this cable between 2 points even at a different height, what happens is that the shape that this cable is taking is exactly that of an hyperbolic cosine. Okay, so this will be an hyperbolic cosine of x. Let's say that this is basically x. Okay, so it is not a parabolic shape, but it is a hyperbolic cosine of x. And this is the fact that this is indeed the case can be proved in a course in calculus of variation. We will do this later. But for the time being, just let's keep in mind that this is what happens if you attach an extensible cable between 2 points at different heights, of course also at the same height is the same. The same happens if you have the cable attached between 2 points at the same height. What you get is not a parabola as you might think, but the shape that you get is exactly the one of an hyperbolic cosine. So this would be again an hyperbolic cosine of x.